Okay, off we go. So here's where we were. Oh, this thing didn't get turned on yet. Okay, let's see. Is that going? Yeah, okay. Now let me just check real quick. Okay, we're still recording. Okay, so here's where we were last time. So we were talking. Okay, we need to get started. So here's where we were last time. We were talking about the single variable chain rule. And again, our purpose here is not to teach you single variable calculus. I know you know single variable calculus. Just as a reminder, the purpose here is to set up a particular point of view that extends most naturally and conveniently, I think anyway, to the multivariable setting. So the point of view I'm taking here is that the chain rule is about composing two functions, right? And we're specifically going to interpret the derivative of these functions as being the factor that you multiply by input change to get the output change. But let's just streamline things as much as possible. Derivatives are factors. They're multiplicative factors. So when you have two functions and then you compose them, and if you want to know what's the derivative of the composition, in other words, you want to know in some sense what is the overall factor that you multiply by there. Well, the overall factor, I think a pretty reasonable appeal is that it's the product of the individual factors. I mean, this is based on the, I think, pretty easy algebraic concept that factors multiply. Right? If you multiply by 2 and then subsequently multiply by 3, you have altogether multiplied by 2 times 3. So, easy observation. So if we take that point of view on the single variable chain rule, and I think this is about where we left off last time, and while we're here, I'm going to point out, I think this is a nice little pithy little point of view. When you take derivatives, you're turning compositions into products. Right? This is the derivative of a composition. Notice the result is that it's a product of the individual derivatives. Okay, so this point of view, now let's apply all of these ideas to the multivariable context. And now again, even though this is a pretty different setting, right? We've got multivariable functions, vector valued, outputs. It remains that a derivative is a factor. Now it's a matrix factor in this case, right? It's a matrix that you multiply by a input velocity to get an output velocity, right? But yada, yada, yada. It's a factor. It's something that you're multiplying by. So don't get lost in the details of, input velocities and output velocities. It's a multiplicative factor. So again, if we look down to the, what happens when you compose functions, if you're composing one multivariable function with another multivariable function, that's a complicated picture. Yeah, sure, totally. But when you compose them, and when you want to understand what is the factor, the overall factor that I have to multiply by with a composition, well, that overall factor is, again, I think it's a pretty easy pitch. It's the product of the individual factors. If I, just to get explicit about it, if I start with some vector x prime, and I want to turn it into y prime, and then I want to turn that into z prime, all right, well, I'm going to multiply by df, and then I'm going to subsequently multiply by dg. Altogether, multiplying by the derivative of the composition is, well, the exact same thing. It's the result of first multiplying by df and then multiplying by dg. So, same basic idea. Now, you're going to notice that the way this is all written on the page here in the notes is deliberately highly analogous to how I wrote it all on the page for the single variable case. It's morally the same idea. Right? I think there's a lot to be gained from looking at this, again, narrow, very particular point of view on the single variable chain rule, even if it's not your favorite point of view on the chain rule. Take this point of view on the single variable chain rule and notice how it extends to the multivariable setting in a snap. Okay, how are we doing on this? Everybody willing to buy this? What we get here is actually a very powerful statement about multivariable derivative matrices. Multivariable derivative matrices multiply. And so again, we are turning a We are turning a composition into a product. Just like in single variable. All right. So let's see an example of this. Now, there's a lot of setup that goes into this example, so bear with me while I talk through all the... Yeah. Oh, yeah. Okay. Yep. All right. So, so a lot that needs to be set up here. You'll notice I have a composition of functions here. Well, I've listed a couple of functions, and they're implicitly composed because look at this. What comes out of the first one is what goes in to the second one. And that's what a composition is. Right? So we have this composition of functions. The composition itself is a function that takes x1 and x2 as the inputs and gives z1, z2, z3 as the outputs. All right, now various bits of information are given about these functions. We'll come back and look at all those details in a minute. We'll use them as needed. But what the question is going to be about is step 1, we want to compute the derivative matrix for the composition. And then step 2, which let's sweep this under the rug for the moment. We're eventually going to want to compute a specific partial derivative of that composition. We'll come back to that in a minute. Okay, so how to compute the derivative of a composition? Well, we're just going to cite this formula right here. Derivative of a composition is the product of the two derivative matrices. And so here that is, right here. The derivative of a composition is the product of the individual derivatives. Okay, now there is a weird little thing here that deserves to be discussed. Notice the derivative of the composition is evaluated at the point 1, 2. The derivative of f is evaluated at the point 1, 2. The derivative of g is evaluated, not at the point 1, 2. It's evaluated at the point f of 1, 2. What's going on with that? Wouldn't we want to evaluate all these functions in the same place, right? At a casual, quick glance, you would think. If you look a little bit more carefully at our picture, and let me zoom back out, a little bit more, here we go, a little bit more carefully at the picture. Let's think about where, in general, should we think in terms of evaluating a derivative matrix. So looking first at the derivative matrix for f, well, a derivative matrix for f turns input velocities into output velocities. Where am I when I am moving with velocity x prime? In other words, if I'm thinking in terms, I'm moving with velocity x prime and I want to know what is my output velocity y prime. Where am I? Well, I'm at whatever this point is in the domain. That's where I am. That's where stuff's happening. That's where I compute everything in question. That is the point where I evaluate df. Okay, so that's the big idea, the first big idea. When you're looking at a derivative matrix, you evaluate at the point where you're at. Okay, so let's look at the composition. The composition takes this as the input velocity and gives that as the output velocity. And when I'm, again, moving with velocity x prime, I am at the point A. So the derivative of the composition also evaluated at A. Okay, now let's think about dg. dg turns that as the input velocity into that as the output velocity. And where am I? Am I at the point A? No, not even close. Look, A is way over here. G has never even heard of that point. Right? G takes points out of this intermediate space and gives you points into this target space over here. G is evaluated at that point, which is presumably the point that f spits out when x is at this point A. So this point is f of A. And so dg is evaluated at f of A. So again, when you look at the picture and really think about what's going on and what are these derivative matrices, what do these derivative matrices do, and therefore where are they evaluated, it actually is, I think, pretty almost automatic. I mean, it kind of has to be this. It wouldn't even make sense to talk about evaluating anything pertaining to G other than where I am in the domain of G, right? And that point over there in that other space just wouldn't make any sense at all. Okay, yeah?
Yeah, since these are like derivative matrices,
Uh-huh.
you just start, like, to get the derivative matrices before even plugging in, you have to go through the process of getting the...
You got to compute a whole bunch of partial derivatives and assemble according to the usual rules. Yeah.
Okay.
And so the really cool conclusion is that when you assemble those derivative matrices according to those usual rules, compositions multiply.
Yes, it's matrix multiplication.
Really cool result. That's right. Absolutely. Okay, so so that's where we were. This is our chain rule, and again, as it should be, DG is evaluated at f of 1, 2. So now I'm going to go back to the statement of the question, and of course we better have these matrices on hand. It's not like I have formulas for f and g. I can't actually compute their partials. I can't actually assemble their derivative matrices from from the first principles because I don't have the formulas. But what I can do is cite what I'm given. And now, I need DG at the point f of 1, 2. Notice, conveniently, we are given that f of 1, 2 is 310. And so, lucky break, the DG that we need is exactly the DG that we have. Everybody happy? Okay. Even easier for the other one, df of 1, 2. Well, I was straight up given that, so boom, that's this. And then you matrix multiply a little bit of arithmetic. I'm sure y'all can do that. And there's your derivative matrix. Okay, so very plug and chug. Let's see here. Now, there is a landmine here I want to point out. I created this landmine on purpose. I do this kind of thing on exams on a regular basis. It's not because I'm mean. It's because that's my job to distinguish between students who know what's going on and who really understand how things work versus students that are kind of just playing fast and loose with, I think you just kind of do the, superficial understanding. So I gave you the DF matrix and the DG matrix, but the DG matrix has to go on the left, but I gave it to you on the right in the statement of the question. And the DF matrix, I gave it to you on the left, but it has to go to the right in the computation. So now as it stands, if you were to have just written down DF times DG, then of course the puzzle pieces, the Legos don't fit together there. You can't multiply those matrices. That would have been your giveaway in that case that's in the wrong order. But had the numbers worked, had the dimensions of these matrices been such that the pieces fit together in either order, this would have been a risky little situation. Right? So I want you all to make sure to get this straight. The order matters, right? Matrix multiplication is not commutative. So you got to multiply them in the right order, and that's your job, right? That's part of the question answerer's job is to multiply these matrices in the correct order. And again, what is that correct order? Well, you can see it from the picture. Whichever function acts first has to be the matrix that acts first. And it's so annoying that notations are kind of conflicting in this way, but when we write diagrams left to right, the one on the left acts first. But when you're multiplying matrices, if you imagine multiplying these matrices times vectors, the vectors are on the right, meaning the matrix on the right acts first. It's on the left in the diagram, it's on the right in the algebra. Heads up, little landmine that you have to worry about, so please do be careful about that. Again, that's just part of how the chain rule works. Okay, Right. Let's talk about the individual partial that we were asked. Right. So let's see here. We were asked. Oh, actually, I do need to keep all this on the screen. We were asked to compute also the partial of Z3 with respect to X1. Okay. Well, let's think about this carefully. Z3. There it is. It's my third output variable. Now, recall, output variables, if you think about the structure of a derivative matrix, right, very rigid, very particular, output variables correspond to rows. So if we're looking at a partial of the third output variable, we need to look in the third row. And so I'm going to be looking for one of these two numbers right here, and which one we'll figure out momentarily. But it's definitely going to be a number in the third row. Notice also we're taking a partial with respect to x1. x1 is our first input variable. Remember as well, the structure of derivative matrices. Input variables correspond to columns. So first input variable means first column. So if I'm interested in that partial, then I need the entry in the first column and third row. That's this number right here, which is 3. Everybody good? Yep.
Could you please repeat why it's the output is a row?
Well, so this is just the definition of a derivative matrix going way back. So roughly speaking, we have to define the derivative matrices that way so that linear approximations will work, which is so that we can interpret derivative matrices as multiplicative factors. It's just sort of underneath everything that we've done. Okay. Yeah. So, yeah, input variables correspond to columns, output variables correspond to rows. Okay. Yeah. So that's back in the section on linear approximations. Yeah. Okay. A couple of special cases. I don't want to oversell these special cases. These are cute observations, I suppose. But I feel like it's necessary to say, but I don't think it's necessary to dwell on. So here we go. Chain rule. Here's a composition of functions. Here you go, composition of functions. And the special case that I want to talk about is what happens when there is, in fact, only one original input variable. And how does that, what does the chain rule turn into when, in fact, there is only one original input variable? So, okay, well, let's look at the first function. Here's the first function's derivative matrix. Keep in mind, input variables correspond to columns. So, if there's only one input variable, then there's only one column. So that's kind of cool. The other thing I want to point out, let's think about what kind of a function this is, right? I've got x, several coordinates, several variables, x, functions of a single input. You might say position as a function of time. That's a parametric curve, right? So I can think of this as a parametric curve in Rn, at which point the derivative matrix we talked about last time in 3.1 is the velocity of that parametric curve. So a really nice interpretation. You can think of that matrix in this special case, one input variable. It's actually the velocity vector of a parametric curve in Rn. And so let me sort of redraw it. Wrong color. This, in fact, is just a velocity vector in Rn. And then analogously, let's look at the composition here. The composition, again, one input variable, again, one column then in its derivative. Again, we have, in fact, position, now position in Rm, as a function of time. So again, with the parametric curve, again, this is a velocity vector. Now a velocity vector in Rm. So that is a velocity vector in Rm. So now let's ask the question, what does the chain rule tell us, or what's the interpretation that I'm going to make of what the chain rule is telling us in this case? Apparently, chain rule tells us that the derivative matrix of f is what you multiply by input velocities to get output velocities. And I'm going to say this is something we already knew. Right, this was our big interpretation of derivative matrices. This is why we call derivative matrices the derivative. Because they do what derivatives fundamentally do. They turn input changes into output changes. And so again, it's a little bit of a weird thing to talk about. We already knew that fact. I think it's cool, though, when a new theorem that we have has a special case that's something that we already knew. If nothing else, it's kind of reassuring that our theorem isn't nonsense, because at least it works in certain cases that we know. Yes?
What exactly is df?
df is the derivative matrix. It's this matrix of all the partial derivatives. It's the thing that makes the linear approximation formula work. It's the thing that, as we established in 2.3, that multiplies by input velocities to give output velocities. Yeah. Yeah. Yes.
So you said the dx dt is velocity, right?
Yeah, that's right. This is the velocity vector of a parametric curve in Rn. That's right.
And then this one is
It's a velocity. The blue one here, this is the velocity vector of the image parametric curve in Rn.
Okay.
That's right. Yeah. All right. Okay, so look, I've got an example here, but I think this example is highly readable. So again, tough choices and all that. I'm going to let y'all mostly read this example. Also, this example could totally be an example in section 2.3. I'm actually not entirely clear why I even have this example in here, but I suppose it's good to have more examples as opposed to less. But let me just point out, even though y'all are going to read most of this, we got to put in a little bit of labor to actually compute that derivative matrix. But the punchline of how we're going to answer this question is we're going to use the derivative matrix and multiply by input velocity to get output velocity. Because that's what derivative matrices do, right? Again, per section 2.3, and as we've revisited in this section. Okay. All right. Now here's another special case. This is a special case of our previous special case. So it's a special case. So our original special case was one original input variable, and again, we know it means that we only have we have one column there and also one column there, just as before. Now I'm going to entertain, what if I also only have one eventual output variable? In other words, what if this f function here, what if it's real valued instead of vector valued? And how does that change things? What does it look like, and are there any convenient sort of rephrasings that come as a result? Okay, well, again, in the same way, analogous to input variables corresponding to columns, don't forget output variables correspond to rows. So that y is the output variable for the composition. So the composition derivative matrix only has one row, which, by the way, it should, because the composition is literally a single variable derivative, one input, one output. There is only one element in its derivative matrix, right? So good, as it should be. But furthermore, notice it's also the output for f, and that means that df only has one row. And now what that means is the chain rule becomes a statement here about a product of a derivative matrix with one row and a derivative matrix with one column. And I just want to remind y'all of an old fact from linear algebra, that if you have a single row matrix times a single column vector, that's literally a dot product in terms of how the computation works out, how the arithmetic works out. And we've made this observation before, that when you have a single row derivative matrix, effectively you're just dotting with the gradient vector. So the punchline of this example is, again, this is not a deep point. It's almost kind of a familiar point. But in the real valued case, you can rewrite a derivative matrix as dot product with the gradient. So, again, a kind of a rehash of old news, and another example that's highly readable. I'm going to, again, let y'all read this for the details. And again, the only reason I have this in here, it's, again, this could have been in 2.3. I'm just wanting to point out that there's the dot product with the gradient that effectively allows us to turn an input velocity into an output velocity. Yeah, yes.
Quick question. If we take the dot product, it means that we're going to get a scalar.
Yep, that's right.
In the previous example, it was a vector, right?
Yeah, oh yeah, absolutely. So this you can't write as a dot product because you look at this right here, it's just straight up not a dot product.
Yeah.
Right, absolutely.
And so that's something to distinguish the special case.
Yeah. That's right. So you have to use matrix notation when you have vector valued outputs. You can still use matrix notation if you have real valued outputs, if you'd like. But when you have real valued outputs, you have the option of rewriting as a dot product if you'd like to for whatever reason. And sometimes that's nice.
So it only applies when we have single row of the derivative matrix. And
In this special case, exactly. Exactly in this special case, yeah. Okay, here's a different point of view. Completely different point of view on the chain rule. And there's some really nice things about this, some really nice pros and some really dangerous cons. Okay, so this is a little bit of a minefield, but it's totally worth it. The payoff is 100% worth the risk. So I am going to show you the result, but then we're going to also talk through some of the dangers. Okay, so here's our situation. Starting off, we have a couple of functions. You notice that what goes out of the first one is what goes in to the second one, so we're clearly composing. And we already know that the chain rule is a statement about products of derivative matrices. And all I've done here is write out some of the actual elemental partial derivatives inside of those derivative matrices. So here's the reason we want to do this. When you are interested in a composition, sometimes all you want to know is one particular partial derivative. Right? Now, not always. Sometimes you need the derivative matrix, and if you need the whole derivative matrix, then oh my gosh, you should 100% use the matrix form. That does a lot of the bookkeeping for you. Yes, it's totally awesome, very convenient, and absolutely what you should do. But if you only need one partial derivative, what are you going to compute the whole matrix when you only need that one element? That'd be super inefficient. No one would ever do that. You're just going to notice if all you want to compute is that one element, well, I compute an element of a matrix by noticing what column it's in. That tells me what column of the right matrix to use. And then you're going to notice what row it's in, and that tells you which row of the left matrix you're going to be looking at. And you compute the desired element of the product by dotting row dot column. Again, that's just matrix multiplication, right? Ancient history, old news. Everybody remembers that from linear algebra class? Everybody content with that? Now I'm just going to write those elements down. You know, how do you actually write down that multiplication? And it's this right here. So it's a handy little single formula. What's nice about this is, again, I don't have to write down an entire matrix of, two entire matrices of stuff, most of which I don't even need. And then compute an entire matrix of dot product elements, most of which I don't even care about, right? This just gets right to the point. If I want to compute that specific element, that specific partial, then I compute exactly these partials and combine as indicated. Very efficient and right to the point. Okay, and here's the first landmine. When you write this down, you start to write this down. And let's imagine as we start to write this down, I say, okay, this partial is, and then I write that down. And then I got to pause and stop and say, hey, wait a minute. that and that, aren't they the same? Can't I just kind of cancel away there? And then check out what I get. I mean, I get that is exactly that, and I have this there, that's exactly that. Oh my gosh, I don't think I even need the rest of that equation. Let's just throw away all that. And this little quickie cancellation, and boom, right, I got it. Very tempting. Everybody see the temptation? It's very tempting. And it's super wrong. Right? And the way we know it's super wrong is because we've already talked about, I mean, look at the chain rule. The only motivation we have for a chain rule is by matrix multiplication because of the argument about velocity vectors and multiplication of factors. I mean, we know this is right with all the terms. And this idea that I can just, let's just kind of throw a bunch of those away, kind of obvious nonsense. But still worrisome because as of the moment, it's not clear what's wrong with this reasoning. Right? So what I want to do now is address this question of why can't I cancel the y's, the partial y's. And it's a subtle point. And I blame the notation. And this is just a difficult reality. First of all, notation is what it is. It's deeply embedded in the culture. We're not going to change it. Just get used to it. It's not going anywhere. The other thing is I'm not clear that I have a practical, better idea for what the notation is going to be. And I was telling somebody in office hours, I've already forgotten who it was, but when you're dealing with increasingly sophisticated objects, a fully explicit notation would be just tremendously bulky and impractical for common use. So, nevertheless, I kind of blame the notation here. So here's ultimately the problem. This notation makes it look like we have a fraction, right? You see the little horizontal line? It looks like a fraction. When you see a fraction, you're tempted to think that you're looking at a ratio of two independently well-defined things. And in this case, we are not. In particular, I claim that this little thing here that you might call partial y1, that is not a thing. It's just not. That partial y1 and this partial y1 are different. In fact, not only are they different, they're not even part of the same story. They live in completely different, contradictory scenarios. You cannot cancel them. So let me be a little bit explicit. When I say they're in contradictory scenarios, if you think about where this comes from right here, this idea of this partial derivative, well, we're taking a partial with respect to y1. Just a quick reminder, what is a partial derivative? Partial with respect to y1 says that I'm going to insist that the other y variables all be held constant. Yeah. So for this to make any sense at all, I have to insist that in that scenario, the other y variables are all constant. But now let's look at this story over here. In that story, I'm taking a partial with respect to xj, which means xj is going to be changing, which means all the y's are going to be changing. They are not going to be constant. So again, it's not that these are different parts of the same story. They're not even in the same story. Does everybody see what I'm talking about? You 100% absolutely cannot cancel these things. They're totally different. Let me say that differently. Even if they were independently things, they couldn't possibly be the same things. Okay, so it is unfortunate that the notation makes it look like they are. And again, landmine. And I have seen this happen on exams, oh my gosh, so many times. I have seen students write down this and be like, oh my God, it works. I'm done. Right? And then they don't write this down and this, oh God, and then it makes me cry a little bit because this, I'm sorry, but it really this underscores that the student does not actually understand the chain rule. Right? So really, really, really wrong, and it's a real catastrophe. So make sure you don't step on that landmine. Real easy to do, and as with many other things that I go on at great length about, I go on at great length about it because I've seen over the years, the bigger of a deal I make, the fewer students step on the landmine. So one of these days I'll get it down to 0. We're not there yet. Okay, careful with that. Okay, how are we going to make sense out of this equation? And for whatever it's worth, this is a really nice way to make sense out of this equation. This equation is about computing an element of a derivative matrix with a matrix product, and that's nice and all. But the problem with this is you got to keep in mind, in the real world, in practice, right? The scenarios where you're going to be using the chain rule in engineering classes or what have you. Frankly, most of the time, your input variables, they're not going to be called x1 through xn. And these intermediate variables are not going to be called y, and these output variables are not going to be called z. They're going to be called other stuff, right? And if you're doing economics, they're going to be like k and l and p and stuff like that, right? And if you're doing engineering, then they're going to be whatever notations are being used for the efficiency of the engine and the power and the heat and stuff like that. So you can't just memorize this equation because it's always going to look different every time, depending on what the variables are. They'll always look different. But you also don't want to have to write down bulky derivative matrices every single time. It's tedious. So here's what I suggest. Totally different point of view on this equation. I like to think of this equation as coming from looking at how changes propagate along paths. Now this is just a take. It's just a point of view. But let's think about if I'm interested in how Zi changes per unit change in xj. Whoops, I wanted to check that. Well, partial derivative with respect to xj means I'm going to hold all these other variables constant. And now let's think about how, in this diagram, when I change xj, how's that going to make Zi change? And the short version is, well, look, when you change xj, that's going to, wrong color. When you change xj, that's going to cause y1 to change. And the act of y1 changing all on its own by itself will cause, to some extent, Zi to change. And then furthermore, xj will cause y2 to change, and that will contribute to how Zi changes, etc., etc. And then it'll cause ym to change, which will contribute to how Zi changes. Right? So we're going to have a bunch of different paths. You can see the paths right here. The paths always go through one of these intermediate variables. Each path represents one way that changes can propagate. Okay, now for each path, what do we get? Let's think about this first path here. Like so. Well, when xj changes, let's see here, colors. As xj changes, that's going to cause y1 to change. And let's think about how, what is the factor here? What is the factor that I multiply by xj's change to get y1's change? Well, that factor, that's the definition of the partial derivative of y1 with respect to xj. Okay, now, fine. Okay, but having happened, if I want to understand y1 by itself, we'll get to these other y's in a second. By itself, independently of the other intermediate variables, as y1 changes, what's the factor that I multiply to get how much Zi changes? Well, that is called partial of Zi with respect to y1. Is that cool? Yes.
Quick question.
Uh-huh.
According to the order that you give us here, does it matter that it's the opposite order of multiplication there?
No, because these are scalars, and so yeah, you can do that. Yeah, those are just regular old real numbers because. Well, overall, this is a dot product, but these two things that you were asking about, yeah, these are literally scalars, and so yeah, you can write them in either order. Yeah, right. Okay. Okay, so cool. So I think this is pretty believable, that this term here is just kind of a representation of how much the change propagates along that path through the y1 variable. And a couple of things you'll notice about this pattern here. You'll notice that the path goes through exactly one intermediate variable. That intermediate variable shows up in exactly the same way in these terms every time. And furthermore, that is always the same as that, and this, wrong color. This is always the same as that. So the structure of these terms always looks alike, and you always get a term corresponding to every path corresponding to every intermediate variable. Right? So what I'm going to be commonly doing, this is pretty common terminology, I'm going to call this the y1 term corresponding to the y1 path. And you can do the same thing for every other path corresponding, in other words, to every other intermediate variable. The y1 intermediate variable gives that path and this term, et cetera, et cetera, et cetera. And the ym intermediate variable corresponding to that ym path gives that ym term. Right. So the beautiful thing about this is you can construct your own coordinate-wise chain rule simply by looking at this diagram. Set up your diagram according to your circumstance, according to whatever the variables are for the functions you're composing, and just generate the chain rule that you need as you need it, based on this point of view. It's very efficient and very convenient. Okay, let's see an example of this. Here we go. Okay, so again, we're composing because the outputs from F are the inputs to G, and I have some explicit formulas given there. And now let's think about how these functions show up. The first function takes x's out and takes x's in and gives y's out. There it is on my diagram. Those y's then go into G and spit out z's, like so. There's my diagram. Now there's a bunch of arrows on here that I haven't drawn because I'm not going to need them, but yeah, there's an arrow there and an arrow there and there and there. A bunch of arrows that we're going to end up not actually caring about. Just to keep things simple, I only drew the arrows we're going to need. Notice the question asked us to compute the partial of z2, there it is, with respect to x2, there it is. So there's my input variable, there's my output variable. Let's talk paths. Well, there's two intermediate variables, y1 and y2, corresponding to two paths, corresponding to two terms. And so, I don't have to know the formula from above at all, just kind of understanding this idea of paths corresponding to intermediate variables corresponding to terms. That is this, that gives this, and therefore this partial derivative computed from this chain rule. Everybody good? And then turning the crank. So note explicitly we have a formula. Let's see here, right here for z2. Z2, it says right there, is y1 cubed. Right? So if you want to know how do I compute the partial of z2 with respect to y1, okay, well, there's z2. Compute its partial with respect to y1, 3y1 squared. Like so. How we doing? Everybody buys it? Yes.
So if you just given like the here.
Mm-hmm.
Could you start like with the opposite because you say that the order?
Yeah. Addition is commutative. You can write the terms down in the other order if you want.
No,
It
I'm
doesn't
talking
matter.
about like having the partial with respect to x2, and then times the partial with respect to y.
Yeah. If you wanna. Yeah. Again, these are scalars, and so you can multiply the scalars in either order.
Okay.
Yeah. Yep. Suit yourself. Yes.
Sorry, how did you get those values at the bottom? The 3y plus 1 squared minus 1.
Yeah. So z2 is y1 cubed. So that means that z2 is y1 cubed. And so computing this partial, I'm literally just going to compute the partial of y1 cubed with respect to y1, and that's an easy partial derivative. Yeah. All right. Okay, here's another landmine. Something to watch out for. Confusion of variables. I know y'all know single variable calculus. Y'all know that I like analogies. And I think it's a powerful tool in learning multivariable calculus to think about what is the single variable calculus version of this, and then to kind of expect that, as is very often the case, it might be, just kind of the same thing. Right? So, silly calculation. Here's a couple of single variable functions. I can talk about composing them. I can ask what's the derivative. Now, I'm going to deliberately screw this up in an obvious way by playing way too carelessly with a single variable chain rule and claiming that the derivatives are compositions, the product of the derivatives, and just writing down g prime times f prime. And I obviously get a wrong answer here. Clearly wrong. Now, one point of view on what I did wrong there is that here's the more careful statement of the single variable chain rule, accounting for the fact that, of course, the second function's derivative has to be evaluated at the output of the first function. And I tell you what, this works. Yeah, sure. That goes in there, and the algebra works out, and you get the right answer. But it's clunky. I think it's clunky. I've always, I understand why. I've understood why since I was in high school, sure, but I still feel like, but I don't like it. Right? So here's what I eventually realized is the much cleaner, much more natural way to deal with this, and that is to recognize that the way the question was written in the first place stinks. Oh my God, this is so wrong. Look at this. We've got this function, f is given where x is the input and the output doesn't have a name. I'll just leave that blank. And then, but g is written where x is the input to g. But if x is the input to g, then it's also the output from f. The way this is written, it looks like x is both the input and the output of f. Nails on a chalkboard. Right? That ain't right. That's unnatural. At best, this is highly undesirable. So here's the good news. This is so easily fixed. And I don't know if y'all saw this in a single variable calculus class. Maybe you did, maybe you didn't. But I think the much better way to do this is to recognize that, look, if x is going to be your input to your f function, well, let's give a different name to the output. Let's not call the output x. That would be outrageous. And if we decide that we're going to call that output y, then that has to be the name that I give to the input to g. Which means that when I write the formula for g, I can't do it like that. I should rewrite g like this. I should not use the same dummy variable for both of the functions. Completely unnecessary. Let's just write g in terms of this different dummy variable, y. And now there's no confusion of variables in the first place. Now there is no worry about, where am I going to evaluate these derivatives? The dummy variables do that for us. Everything's automatic. Turn your brain off, proceed blindly, it'll all work out. It's like having rails as you're bowling, right? You cannot throw a gutter ball with the rails, and you cannot screw this up because it will keep track for you. And notice, just to demonstrate that, here I've written the single variable chain rule, again, carelessly, right? No, not worrying in the least about where I'm evaluating what. And those derivatives, naturally, because I avoided confusing my variables, those derivatives are naturally written in terms of variables that I understand. And because y is my input to g, y is also my output from f, and that helps me see that this y here is in fact just x squared, and that allows me to get to the right answer. So, longer than I intended to talk about single variable confusion of variables, but don't confuse your variables, right? I mean, avoid confusion of variables if you possibly can. And next time what we'll see is how the exact same thing happens in multivariable. We'll pick up there on Monday. Y'all have a great weekend. See you later. Don't forget about attendance. Make sure to come talk to me if you didn't already get marked off.